Rennselear sorry. Hi, my name is Kevin Rose. I'm an associate professor at Rennselear Polytechnic Institute. And Pete, you want to?
Yeah, and I'm Pete McIntyre, an associate professor in the Department of Natural Resources and Environment at Cornell. So yeah, it's really a pleasure to be joining everybody today, and truly it's especially a privilege to talk to the council about this topic, because we wouldn't be having this conversation if it weren't for the good work of the council and Willie Janeway's leadership across about 2.5 years at this point. Kevin, maybe I'll kind of do some of the intro slides.
Perfect, yeah. And we should mention, or maybe Pete was gonna, probably was gonna do this, so I'm probably cutting him off, but we want to mention, so this process is very fluid. This is ongoing. So while we're recording this, also we want people to realize that plans are not finalized. You know, we're going to talk about, for example, a consortium of partners, but that consortium is nebulous right now. As we know that a lot of people were invited to a workshop last summer, and there's a lot of organizations involved in this that will describe some of them. But what the path we take moving forward here is going to depend on people's time, availability, funding priorities, etc. So we're not really sure where that ends up going. So this presentation sort of highlights where we've come from, where we might go, but it is not set in stone on where exactly all of this goes.
Absolutely, and kind of in that, in the spirit of this being a work in progress, we certainly do welcome questions. We've got a slide deck of maybe 12 or 13 slides, but there's going to be plenty of time at the end for discussion. Yeah, so we're calling this project SCALE, which is an acronym for a survey of climate change and Adirondack Lake ecosystems. And as Kevin said, the notion here really is that kind of centers on a cooperative or consortium approach. And that's because the spatial scale, as all of you know, of the Adirondacks is very extensive. And then it's, you know, we're talking 4,000 plus lakes. And we're also trying to be equally expansive in the scientific approaches that we take to figuring out how climate change is impacting Adirondack lakes. And so to do that, it doesn't take just RPI and Cornell or just the council or any one organization just can't cover all the bases. And so from the start, we've had an agreement with the council and with a number of NGOs and a wide range of academic partners and agency partners that we really need a team approach to resurveying Adirondack lakes. And so as Kevin mentioned, in July 2021, we, with courtesy of funding from NYSERDA, we were able to organize a meeting over in Saratoga Springs where we had representatives from all of these organizations. And that's not to say that there aren't others that certainly have strong interest and credentials within the Adirondack space, but we're trying to get together just as a first meeting many of the interested parties, and especially those that have kind of different perspectives and different toolkits or skill sets to bring to bear on the current state of Adirondack lakes, and also trying to look both forward and backward at what lake conditions might be. So NYSERDA was willing to kind of support this seed effort back in July. We're finishing up the report on that now. And the motivation here was to build upon the amazing work done in the mid-'80s across the Adirondacks. There were 1,469 lakes, which is really, in lake ecology by lake ecology standards, that is a remarkably broad and deep survey. And it wasn't just a quick visit to the lakes. They were surveying the morphometry, the chemistry, and a range of different species groups within all of these lakes. So that was motivated by, the work in the 80s was motivated by acid rain. So the big question was, how is acid precipitation affecting these lakes? Is that mediated by the landscape and the shape of the lake itself, the bottom of the lake? Is it mediated by the chemistry of the watershed and of the lake's waters? And how does it play out in terms of the plankton in the water, both the animal and plant plankton, and then the fish that that depend on that base of the food web. And so they surveyed this vast number of lakes throughout the Adirondacks. They classified each lake in terms of its vulnerability to acidification based on its chemistry. They looked at the evidence of impacts. So the thing that was amazing there was linking the kind of what the lake is like in a physical sense to the chemical impacts from people, and translating that all the way through to fish communities and fishery resources. So they did about 400 lakes per year. It was an immense effort across several years of sampling and then several more years of data synthesis. And the results of that were really compelling at addressing acid rain. This is truly a pioneering effort that became the gold standard for understanding the way that acid rain impacted the waters of the US and beyond. So for instance, to just highlight one example of the kind of results, this is the acid neutralizing capacity, a measure of the chemistry of the water and its ability to soak up acid inputs without becoming fundamentally acidic. And so if you're at 0, the system has no capacity to sort of buffer those acid inputs. If you're up here above 100, then the system still has substantial capacity for buffering acid rain. And this is the number of fish species. So you can see this nice, what we would call threshold behavior, that in a system that has no buffering capacity, the fish are gone. There's this rapid transition between that no fish state and a good number of fish, a half dozen species. So across this fairly narrow window of acid neutralizing capacity, which is driven by basically the watershed soil chemistry, across that narrow window, we go from a full complement of fish to 0 fish. So it's that kind of insight that you can get from looking at these very broad lake surveys. And it wouldn't be enough simply to go out and, as a fish biologist, to go out and say, well, these are the lakes on the left that have fish, these are the lakes that lack fish. Clearly, there's some level of spatial pattern there, but it's not until you unify the chemistry with those fish samples that you really understand what's going on with acidification. So we're at a similar sort of state as we think about climate change impacts. We don't really have we have a baseline from the 1980s in terms of chemistry, in terms of which species are where. We don't have a very good baseline for the large majority of the Adirondack lakes in terms of understanding how their temperatures may have shifted, how several different key dimensions of their chemistry may have shifted. We've got a few dozen lakes that have been monitored very effectively for decades, and those give us a lot of insight, but we don't actually know then, when you go out to the whole Adirondack scale, how much things may have changed. So these are some visualizations of that 1980s data. And what we would strive for is to actually represent changes in the lakes in a kind of both looking at individual lakes, but also achieving a kind of a more continuous look at what's going on. And these are maps that one of Kevin's students derived from satellite remote sensing. So a key feature of this consortium approach is not only that there'd be a lot of people involved in doing the surveys, and then especially in taking the samples that are collected in a systematic way across hundreds of lakes and analyzing those with cutting edge methods. A really key feature is we're also bringing in 21st century methods. So satellite remote sensing in the 1980s, you couldn't have imagined having a true data characterization of something like the incoming radiation, solar radiation, and its heterogeneity in space, or especially thinking about how that's changing through time. Whereas now with remote sensing technology, with eDNA technology, with high frequency sensors, none of these things were available to us in the 80s. So we really can move from kind of continuing that tradition of lake by lake survey, but also using some of these new tools to get a more continuous or integrative perspective on what's going on. Kevin, you want to take over?
Sure, yeah, and then Pete, I don't know if you can see the chat window, but a question came up about the total number of staff members that the 1980 survey had. Do you recall about how many people were employed in the mid-80s?
You know, I Neither Kevin nor I were there. We were in grade school at the time, so I do not know how many people at the height of the ALSC effort were
Yeah,
involved.
me either. My sense was it was in the 20s, that there were at least well over a dozen people. We did calculate, we got information on the total cost, and then adjusting for cost inflation over time. I think it was just about $11 million in today's money, pre recent inflation, at least as of last summer. So it was a considerable effort. But as Pete mentioned, a lot of it was done with helicopters. Some of it was even done with donkey into more remote lakes and whatnot. But that was all done with the goal of understanding acid rain impacts on lakes. Since then, there's been a lot of monitoring programs, as this slide shows, DEC, and the Adirondack Long-Term Monitoring Program. That did mostly the physics and the chemistry of the systems. There was a complement to that ran for a number of years, called the Adirondack Effects Assessment Program, that focused on the biology of 28 lakes in the Adirondack. So ALTM was about a little over 50 lakes. And then there's USGS, US Geological Survey, does ongoing monitoring. Predominantly, they have work funded from NYSERDA, for example, for stream and river, both long-term at Buck Creek site, as well as a survey of hundreds of streams at lower frequency. EPA has contributed a number of funds as well as sampling efforts through long-term monitoring programs. There's CSLAP program, obviously, probably many of you are aware of. And more recently, there's the New York State Mesonet program as well, and that's predominantly focused on atmospheric monitoring throughout the state, mostly for weather, initially funded by Homeland Security. So a lot of different monitoring programs that have data through the Adirondacks and throughout the broader Northeast to understand long-term trends. But in terms of baseline assessment of where we're at climatologically and potential climate change impacts, we really are lacking that. We have this 1980 survey that was focused predominantly on acid rain, but missing a lot of variables that are important for climate change. You want to click the next slide, Pete? There we go. One data set. So our group has made efforts to try to get historic data made publicly available. One example of this is the Adirondack Effects Assessment Program. As I mentioned, this ran 1994 to 2012. And then the Adirondack Long-Term Monitoring Program is continued ongoing. Recently, this is now a couple years ago, in Leach et al., we compiled all of these data together in a single repository, pushed them out to created an R package and pushed them out to EDI as a publicly available data set, all on with climatological data simultaneously, so they can all be used. As Michael mentioned too, I'll just mention this in case people aren't paying attention to the comments. I can see them, and probably Pete can't if he's sharing his screen. The Adirondack Lake Assessment Program is in the 25th year of monitoring about 50 to 60 lakes. That's my understanding as well. I think there's about 52 lakes total or so. And as Pete's slide showed, this ALTM field operations 2018 to present, so 43 sites now collected on a seasonal basis. And the months are listed there. An additional 15 sites just collected once annually. And the last major update to this, there's a 2019 reference with a link there. Excuse me, that was published summarizing data. So moving forward, what are our big concerns? And going from acid rain to climate change, what are we going to sample differently now, and why do we care? What's changing about climate change, and what are the major changes that we see in lakes? Obviously, temperature is something that we care about, and we have some temperature data already. But often more importantly, are the biotic and the impacts that changes in temperature have on the chemistry and the biology of these systems. One of the biggest, most important changes that temperature can drive is changes in oxygen availability. So all complex life depends on oxygen. And in addition to that, the presence of oxygen fundamentally changes a number of chemical reactions that occur in lakes. So when you get the loss of oxygen, termed anoxia, you'll get changes in massive increases in methane production, for example, changes in mercury cycling, changes in nutrient loading, and what's referred to as internal loading of phosphorus, which is often a limiting nutrient associated with the potential or increased potential for harmful algal blooms. So all of these chemical and biological changes occur driven predominantly by, can be driven by temperature changes, but it's the non-linear and changes in temperature, both between, so increasing temperature reduces the solubility of oxygen in water, but when you warm surface waters, you reduce the mixing of oxygen to deep waters. And by losing ice earlier in the season, what's referred to as stratification, as lakes are stratifying earlier in the year, we're seeing increases in the onset of stratification. So those different density layers separate earlier in the season. The deep waters are then separated from atmospheric exchange and renewal of oxygen for longer periods of time. So by late summer, we're seeing greater oxygen depletion. The figures on the right show surface temperature, surface oxygen below that, and on the upper right, deep temperature and deep water dissolved oxygen show trends from a paper published last year in Nature, which included 26 lakes in the Adirondacks, but then also about 400 lakes around the world in other locations, mostly in the temperate zone, showing that we've seen since 1980 nearly a 20% loss in dissolved oxygen concentrations. That's enormous, and that's really biologically important and chemically important. In the Adirondacks, for example, the box and whisker plots on the left show what the losses have been in surface waters and deep waters. This is based on 28 lakes, and these median trends are pretty rapid, and you can see that they're actually faster than the trends for the temperate zone lakes as a whole. So A, very fast rates. B, this is only based on 28 lakes, ended in 2012 was where that data set is. So what's happened since, we don't know. And do these 28 lakes represent the broader region throughout the Adirondacks? We don't know. So hence why we're very interested in getting back out and surveying for basics like temperature and dissolved oxygen. And Pete, feel free to add anything as well. And I think, yeah, I can hit these slides. Or do you, Pete, did you want to add anything?
Well, I guess I'll just pop back here for one moment to add that, you know, these units are probably pretty mystifying for those in the audience who aren't limnologists. So just to put this in context, this is on the order of, say, 6 or 7% of the dissolved oxygen typically in a temperate lake, about 6 or 7% loss per decade. So this is really not a trivial, and the data set extends only across a couple of decades and ending in 2012, as Kevin said. So that's far enough in the past now that it's great cause for concern that if this sort of depletion of deep water oxygen was maintained, it could trigger all of those chemical and biological negative consequences that Kevin talked about, the production of both methylate organic mercury that can enter the food web and contaminate the fish, the release of production and release of methane. So lots of bad things that can happen. And these are really high oxygen loss rates. And it's much higher in the deep waters than in the surface waters. So Kevin, I'll hand it back to you here with the algae and the
Sure. This is another trend that we've seen from this long-term, the biological data set that was sampled 1994 to 2012. So over time, we've seen slight increases in chlorophyll concentration over that period. When we're thinking about potential for increases in algal blooms, perhaps, you know, as Pete mentioned, you know, and as I mentioned earlier, with greater losses of oxygen, we can increase nutrient concentrations coming out of the sediments. That's a concern. It's really open and up in the air, though, on how we're going to see productivity changes with climate change. Might we see increases in nutrients in surface waters or increases in algal blooms? Maybe due to increasing temperatures, increases in loading and precipitation. However, also warmer waters lead to stronger stratification, and then perhaps lower nutrients mixing or getting mixed from deep waters into surface waters. So perhaps surface waters will actually become more nutrient depleted over time. So it's a big open question that definitely is worth further investigation, especially given concerns for human health and water quality, just general water quality concerns with increases in harmful algal blooms as documented across New York State. Meanwhile, zooplankton abundance, so this is fish food. This is their intermediate between our productivity of our base of our food web, and this is what our fish are eating, our top predators in our lakes. Zooplankton biomass in this survey of 28 lakes declined substantially, so a 60% decline across all of these lakes. That we think is mostly driven by chemical changes in the lakes. So a lot of lakes are losing calcium. Calcium concentrations have decreased in the lakes over time, and we're now reaching thresholds at which a lot of zooplankton species can barely survive. They need a certain, at least typically about 1 to 2 milligrams per liter calcium in the water. That's becoming increasingly limited. Have these trends continued out? 2012 sounds recent, but that was a decade ago now. And realistically, it's going to be at least another year or two before we actually were able to do a widespread survey. So now we're looking at a long time, even since the last data point was measured. Have these trends continued? Have they amplified, et cetera? So. And
Yeah.
Pete, you want to?
Yeah, so that we've just given you the sort of whirlwind abbreviated tour of what's known or what's suspected. So we're trying to be very transparent here that the truth is we have this small number of lakes in which there has been ongoing monitoring, but a lot of the monitoring wound down, especially when you look across the physics, the chemistry, and the biology, wound down a decade ago. So there's good reason to think that these lakes are changing fast. There's good reason to think that there's a lot of heterogeneity among the lakes in their rates of change. I mean, if we go back just to look at this oxygen trends again, I mean, note that these box and whisker diagrams are illustrating the kind of the central, the average pattern, and then the common range, and then the extremes. So there are cases of individual lakes that are behaving quite differently from the norm, both smaller changes and larger changes. So there's a lot of heterogeneity, a lot of differences among the lakes in how they seem to be changing through time. And nailing down how that, whether that's a consequence of climate change or of the other factors, of other variables that are changing in our world, is actually quite difficult to figure out. But by surveying a large number of lakes, we start to get the power to draw strong inferences about what are the kind of underlying dynamics, how fast are things changing, both on average and the variation around the average. And so coming out of this big initial group meeting back in July, we identified 4 big themes that really made sense as focal topics for a 21st century Adirondack Lake survey. So the first is really just nailing down the rates of change of water temperatures and oxygen levels. So in the last few slides, you saw the kind of synthesis of what's known, but there's a whole lot that's unknown. So we need to do better at that with both empirical work in the lakes and also trying to use satellite remote sensing potentially on some of the larger lakes. So then we want to translate that into the biotic consequences. How are food webs changing? How is the mercury in the fish changing through time? There's a whole host of those knock-on effects from the basics of the climate shifting, then the lake conditions in terms of temperature and chemistry shifting, whole host of knock-on biotic responses. So then the other 2 themes are getting a little more sort of conceptual. So a big priority in New York State has been carbon budgeting. And so initially with leadership from the governor's office and with a lot of momentum behind that now, we're asking questions about carbon budgets for many different sorts of ecosystems across New York State. And historically, there hasn't been much attention paid to lakes, even though we know from studies elsewhere that lakes can be.
Pete, you're muted somehow.
Oh, I must have tapped my mute button. Sorry. how long ago did I go mute?
10 seconds, not much.
Thanks for the shout out. So there's been this recent emphasis on trying to figure out whether ecosystems of many different sorts are acting as net sources of greenhouse gases like carbon dioxide and methane, or sinks for those greenhouse gases. Lakes haven't been studied intensively in New York State for the most part with respect to those carbon budgets. So that's an area that's very timely in terms of fitting into broader state priorities, and where the Adirondacks, because of the large number of lakes, may have a particularly important role to play. And then getting more lake specific, across the entire state and well beyond, within the northern part of the US, these harmful algal blooms are becoming quite prevalent in many, many lakes where we didn't see them before. So we in general think of Adirondack lakes as being pretty sheltered from these harmful algal blooms by virtue of the fact that they're not all that warm, and the cyanobacteria typically prefer warmer temperatures, and they're not very nutrient rich, and the cyanobacteria typically thrive in more nutrient loaded systems. But as Kevin talked about, the temperature is changing, and potentially the background nutrient concentrations due to these internal cycling shifts may be facilitating the conditions that could lead to harmful algal blooms. So something that we didn't think about as being a big deal in the Adirondacks, and we still don't in most Adirondack lakes today, think of it as a current problem, could very well become a looming problem in the coming decades. So doing the groundwork now to set a baseline and to identify which systems and under what conditions are we starting to see harmful algal blooms would be very valuable in this region where the lakes are really sort of a crown jewel of the Adirondacks as a whole. So important for our sense of place, and of course, when you have a harmful algal bloom, it sort of spoils that. So under each of these four major themes, there's a whole bunch of different components. We're happy to talk more about those in the question and answer period. But we're really trying to build on the extent and the rigor of the Adirondack Lake Survey Corporation work in the 1980s, also build on those other monitoring programs since that time, while integrating eDNA technology, remote sensing, all of these amazing little data loggers that are coupled to fairly low cost and high temporal sampling sensors with little computer chips that record the data across months. So you don't have to be there putting an instrument in all the time. Instead, you can just leave the sensor out there and collect it at the end of a season or the end of a year. So the combination of kind of the bird's eye view and continuing across some hundreds of lakes to get up close and personal using these new sensor technologies and eDNA methods. So we're working on a report to NYSERDA that's going to be circulated to the workshop attendees fairly soon. It will become public after it's been reviewed by the consortium members. And so upcoming priorities, so we've had a lot of really productive conversations with the Osable team that have kind of, the Adirondack Lake Survey Corporation has recently merged with ASRI and received seed funding from the state of New York to kind of get the scale initiative launched. And elements of that are going to include mining these historical data sets in order to pick which lakes. We're not going to be able to do 1,469 lakes again. Rather, maybe the high number might be a quarter of that, and that might even be too optimistic. So picking which lakes to do in order to really represent all of that variation in what we know, all the regional variation, et cetera, is going to be a major investment in the next year. Refining the protocols, bringing the teams together in order to be ready to jump after field sampling is completed in the first year. So that first $500,000 has been allocated to ALSC in the FY 2023 New York budget, and we're in midstream and working with ASRI to try to match up the priorities from the consortium perspective to really lay the groundwork for getting scale launched at an even more intensive way in 2024. Kevin, did I miss anything?
No, I think that's great. There was a question on could drones be used for any of the sampling, and I think maybe we can move over to the question and answer portion of this and have a conversation about that too, because Kelly also mentioned she can speak to it from a practical perspective as well.
Yeah, thank you, Kevin and Pete. Just bear with me. I'm going to pause or stop the recording right now, and then we can go ahead and do that.